Okay, this is the sample exam at D2L that I posted. The solutions to this are also posted at D2L. I'd rather just look at my written solutions, but I thought some of you might like to watch me go through step by step in solving these problems. Now, I just want to quickly point out that the equations that are on this practice exam and the other practice exam are the same equations that you're going to get on the front page of that D2L exam. Unfortunately, though, once you go to the second page to start answering questions, you can't go back to the first page where the equations are listed. So once you start the exam, you're not going to have those equations unless you print out these two pages and have them sitting by your computer so that you have those at your disposal during the exam. Or you can take pictures of them, whatever you want to do. Let's start with this problem here. We have Shannon riding her new blue bike. The radius of each wheel is given to be 0.3 meters. She's headed towards a stop sign, and the wheels have an angular velocity, that's an omega, of 12 radians per second. We're asked for the direction of the angular velocity vector for the front wheel at the instant shown. Now, if she's going left, then those wheels are turning counterclockwise from our side of the bike. And we know that the omega vector is given by right-hand rule for omega. And that rule says that if you rotate your fingers of your right hand in the direction the wheel is rotating, it's going to force your thumb in the direction of omega. So we know that omega is out of the page by the right-hand rule. Okay, that was easy. What is the magnitude of the linear velocity of Shannon at the instant shown in the diagram? Well, last Wednesday we talked about a rolling condition, and that rolling condition is that the velocity of the bike is proportional to the angular velocity of the wheel, and the proportionality constant is the radius of the wheel. Okay, and so here I know the radius of the wheel is 0.3 meters, and we're told that it has an omega of 12 radians per second, and that's going to give me a linear velocity of 3.6 meters per second. And the radians can just drop out because that's not an actual unit, that's a placeholder there. Now we're told that when Shannon gets to this tree here, she presses on her brakes, which apply a constant frictional force on the rim of the back wheel. Okay, so that frictional force would be acting like that. And that friction force is 60 newtons. And in 5 seconds, she rolls to a stop here at the stop sign. Okay, the wheels don't skid. She's just constantly in contact with the ground and not sliding. So what is the direction of the angular acceleration vector for the back wheel after she passes the tree? Well, that alpha vector has to be opposite the omega vector for down. Okay, and so if omega is out of the page, then alpha is into the page. Okay. The direction and magnitude of the torque, we know that the magnitude of the torque is just the radius of the wheel, the distance from the pivot to where the force is applied, times that friction force. Well, that's going to be 0.3 meters times a friction force we're given of 60 newtons. So that's going to be 18 meter newtons. Okay, and the direction we can get two different ways. The direction must be the same as the direction of alpha, which would be into the page. We could also get that by using the right-hand rule for torque, where we start from the pivot, that's the axis of the wheel, and we define that position vector that goes out to where the force is applied. So if I draw it big, I've got this position vector, and then I've got the force that is trying to keep this wheel from rotating that way. So that would be my friction force, kinetic friction. Now, if that's my pivot, the right-hand rule for torque has me reach from the pivot to where the force is applied. So I reach with my right hand out to where the force is applied. The most important step is I have to turn my wrist so that I can wave in the direction of the force. Well, that's going to force my right thumb in the direction of the torque. And so again, I start from the pivot, reach out to where the force is applied, turn my wrist so that I can wave in the direction of the force. My thumb is in the direction of the torque, which is into the page. Through what angle in radians does the wheel turn between the tree and the stop sign? Well, this is a rotational kinematics problem, so I make the list of my 5 variables, always the same. And remember, I have to find 3 of these in order to proceed. Well, I know that the initial omega we're given is 12 radians per second. It has to stop at the stop sign, and we're told that it stops in a time of 5 seconds. And so I've got 1, 2, 3 pieces of information here. I'm looking for this angular displacement. That makes the alpha the who cares. So I use the formula that doesn't have alpha in it. That's delta theta is equal to 1/2 omega initial plus omega final times delta t. Omega final is 0 and drops out. And so I get this is 1/2 times 12 radians per second times 5 seconds. That's going to be 30 radians. And how far is the tree from the stop sign? Again, we can use the rolling condition. We've used the rolling condition in this form, comparing the linear velocity to the angular velocity. We also have a relationship between the linear displacement, it's proportional to the angular displacement, again with the proportionality constant being the radius of the wheel. And so this is just going to be 0.3 meters times the 30 radians, and that's going to be 9 meters. Okay. And that was a pretty straightforward problem. Okay, let's look at this torque problem. We have Will. He's on a painting platform, and he's tied that up in a pretty peculiar way, kind of messy there. And instead of using 2 vertical ropes, he's used 3 ropes as shown. We're told that the platform is 4 meters long and that it has a mass of 50 kilograms, or a weight of 500 newtons. We're also told that the tension in rope 2 is, let me get this adjusted here. This is going to be 1400 newtons. That's given in the problem. Now, we want to draw an extended free body diagram for the platform. So let me draw that Now, on a multiple choice final exam on D2L, you're not going to have an opportunity to draw a free body diagram or an extended free body diagram for points, but I would still encourage you to recognize that all dynamics problems start with a free body diagram. If it's a linear problem, you do a regular free body diagram. If it's a rotational problem, a torque problem, you do an extended free body diagram. And so you need to have a lot of scratch paper ready at your disposal there. Now, the first force I put on any free body diagram is the weight force. That's going to be of the platform. And like we said, if this platform has a mass of 50 kilograms, it's going to be 500 newtons. I then ask, are there any magnets in this problem? No. So what touches the platform? Well, I have will pushing down with a normal force on the platform. I have this rope 1 pulling with a tension force. I have rope 2 pulling here. And I have rope 3 on the platform. Okay, and that's my free body diagram. Now, we're asked to find the tension in rope 1, and to do that, we recognize that there's 3 principles that we can use. One, since this platform's not going anywhere, all the force to the left has to balance all the force to the right. Second, all the force up has to balance all the force down. And third, the torques that are trying to make this go clockwise about any pivot have to balance the torques that are trying to make it go counterclockwise. Well, you see that the tension in 1 is all to the left. And so I'm going to use the principle that the F net in the x direction has to equal the mass of this platform times the acceleration in the x direction of its center of mass, but that's 0. Okay? And so that means that T1 has to be balanced by any force acting to the right. Well, the only force acting to the right you can see is the x component of T2. Okay, so that's going to be T2 times the cosine of 53 degrees. We're told that T2 is 1400 newtons. The cosine of 53 degrees is 0.6, and so that's going to give me 840 newtons. Now we need to find the mass of will. Well, finding the mass of will is kind of easy if we only knew the weight of will. And if we drew a free body diagram for will, we've got this weight force on will that's equal to the mass of will, that's what we're looking for, times g. And then we have the normal force by the platform on will. And if Will's just standing there, and that looks like what he's doing, he's got 0 acceleration, that means that this normal by the platform is equal to his weight in magnitude because he has no acceleration. Well, I also know that by third law, the push platform up on Will is equal to the push by Will down on the platform. And so that means if I could find this push by Will on the platform, I would then know his weight, and then if I divide by g, I could get his mass. So let's do that. Now, we might want to think about, well, do I balance all the upward force with all the downward force? Well, I can figure out the upward force due to T2 using my trig, but I don't know the tension in rope 3, and I don't know this push by will. I've got two unknowns, and so I need to get rid of one of those unknowns. And I do that by balancing torque and choosing my pivot to be at the location of the unknown force that I don't care about right now, and that's T3. If I do that, then T3 gives me no torque about that pivot point. And so now what I'm going to do is I'm going to balance all the clockwise torque with all the counterclockwise torque. Okay. Now, how do I choose what's clockwise and what's counterclockwise? Well, again, I use my imagination, and I pretend that a great big golden spike is going right through this platform, right where I've drawn the X. And I pretend that this platform is forced to rotate about that pivot point as if it were a hinge. And then I ask for each of these forces, which are trying to make it go clockwise and which are trying to make it go counterclockwise. Well, T2 is trying to make the whole thing go clockwise around this pivot. T1 is not trying to rotate it at all about that pivot. And the push by will and the weight are trying to make it go counterclockwise. So I can say that the T2 times the sine of 53 degrees times its lever arm of 3 meters is equal to the normal force by will on the platform, times his lever arm to the pivot, which is 3.5 meters, plus this weight force of 500 newtons times its lever arm. Its lever arm is 2 meters. Okay. Now, if I solve that, and again, I know what T2 is. That's my 1,400 newtons. Okay. If I solve that, what I get is a normal force by will on the platform is equal to 674 newtons. Now again, that's going to equal the mass of will times g, where g is 10 newtons for each kilogram, and that's going to give me the mass of will is 67.4 kilograms. Okay. Now we want to know the tension in rope 3. Well, since we've already solved for this push by will, we can now use the fact that the net force in the y direction has to equal the mass times the acceleration, and the mass of the platform, times the acceleration in the y direction, and the center of mass of that platform is not going anywhere. So this time we have two forces in the y direction. We have the 1,400 newtons times the sine of 53 degrees. Okay, that's this vertical component. If this is 53 degrees, that's going to be this vertical component of that T2. And that's up, so that's positive. I then have T3, that's what I'm looking for. It's up that it's positive. I then have the push down by will, which we said was 674 newtons, and I have the push down by the pull down by gravity, which is 500 newtons. And if I do that math, I find that T3 is going to equal 54 newtons. Okay. Now, suppose Will were to move to the location where rope 2 is attached. In other words, we're going to move Will. We're going to move him right over here. Okay. He's going to move to the right half a meter. Okay. And what we want to do is figure out what that's going to do to the tension in rope 3 in this vertical rope here. Is that going to increase, decrease, or stay the same? Well, the reasoning here is pretty sophisticated. We know that if he moves over to the right, and we again choose this pivot here at the right excuse me. I'm sorry, I got a phone call there. So the question we're answering is if Will moves to the right on that beam by a half meter, what's going to happen to the tension in this vertical rope T3? And the answer is, strangely enough, it's got to increase. And the reasoning, as I said, is a little bit sophisticated. If we look at the counterclockwise torque, well, that counterclockwise torque about the pivot on the right end was caused by Will pushing down and the weight force on the beam pulling down. Now, the center of mass of the beam isn't moving, but by moving Will to the right, we've lessened the lever arm there. So this will decrease the counterclockwise torque. Well, if things are going to balance, that means that the clockwise torque must decrease. Well, the only thing giving me a clockwise torque is T2. And so that means, therefore, T2 must decrease. Well, seems like everything is decreasing. Well, one thing is not decreasing, and that is the total force down. The net force in the y direction is still equal to 0, and the weight down is still the same. I mean, the force down is still the same. I still got the weight of the beam. I still got the push by Will. And that's still going to add up to the same, 1,174 newtons. And so that means if T2 is pulling up less, T3 must increase. Okay. Well, let's move on to this buoyancy problem. we have this big S that has a volume of 600 centimeters cubed. It's fully submerged in water. We got H2O here. And those two strings are holding it in place, and they each have a tension of 2.5 newtons. And the density of water, of course, is 1 gram per centimeter cubed. Now, as I've said in other places, you can imagine doing this exact same problem in heavy cream, or some other liquid. And that would be good practice for the exam. If I draw a free body diagram for the S, I'm going to have a weight force, the earth pulling on the S. I have a tension force that is going like that. We'll call that tension in the left string on the S. We've got a tension here, the tension of the right string on the S, and I've got this buoyant force. Okay, and that's my free body diagram for the S. Now, the magnitude of the buoyant force, we just use Archimedes' principle and say that's going to be the weight of the liquid, in this case water, that is displaced. And so that's going to be the mass of the water displaced times G. Okay. Well, the mass of water displaced is going to be given by the density of water times the volume displaced. Now, that's just 1 gram for every centimeter cubed times a volume of 600 centimeters cubed. And the centimeters cubed cancel out. And what I get is 600 grams. And it's going to be convenient to make that 0.6 kilograms. Okay? Now, imagine if this were heavy cream, you would just put a different density here, say 1.5 instead of 1, and you would have gotten 900 grams if this were heavy cream. Okay? So up here, that means that I'm going to have 0.6 kilograms times 10 newtons for each kilogram, and that's going to give me 6 newtons. So the answer here is 6 newtons. Okay. Now, what's the mass of the S? Well, if I knew the weight of the S, I could find the mass of the S pretty easy just by dividing by G. So let's balance this free body diagram. I know that the buoyant force is 6 newtons. I also know that if I have a force, let's take the tension in the right string on the S. I know that that force can be broken up into an X part and a Y part. We'll call that Tx and Ty. And I know that this must be 53 degrees. If this is 53 degrees, okay, and I know that this tension, we're given this in the problem, is 2.5 newtons. Well, that means that Ty is going to equal 2.5 newtons times the sine of 53 degrees, and that's just 2 newtons. Okay? So if I use the fact that the net force in the y direction is equal to 0, then what I have is that in the positive y direction I have the buoyant force of 6 newtons. I also, well, that's all I've got in the positive y direction. In the negative direction, I've got 2 newtons down from the right string and 2 newtons down from the left string, and then I've got the weight force of the S, and that all has to add up to 0. And so I see that the weight force on the S is also 2 newtons, and that tells me that the mass of the S is going to be 0.2 kilograms or 200 grams. Now, if we cut the string simultaneously, the only forces acting on this S are the buoyant force, which is 6 newtons, and the weight force, which is 2 newtons. And so if I use Newton's second law to find the acceleration, my net force, I've got, let's call up the positive y direction. I've got 6 newtons up. I have 2 newtons down, so it's negative. That's equal to 0.2 kilograms times A. And that's going to give me an acceleration of 20 meters per second squared. And it's a positive, so that's going to be up. Okay? So that's my answer there. Now, when the S is floating, what fraction of the S will be above the surface of the water? Well, we know that the density of the S is just the mass of the S over the volume of the S. That's going to be 200 grams over 600 centimeters cubed. Well, that's going to be 1/3 gram per centimeter cubed. And that's going to be 1/3 the density of water. Now, we talked about that iceberg, and if the iceberg had 90% of it submerged, that meant, we showed in class, that the density of the ice was 1/3 the density of the liquid. And so here we have a density for the S that's 1/3 that of water. So that means that 1/3 of the S will be below the surface. Well, we're asked how much it will be above the surface. So 2/3 will be above. Okay, let's stop here. Okay, let's look at these multiple choice questions. This first question: a ball is thrown straight up with a velocity of 30 meters per second. How high above the starting point will it travel before stopping? This is a linear kinematics problem. Let's choose up to be the positive y direction and down to be the negative y direction. We make our list of variables. And because this is free fall, we can immediately put in negative 10 meters per second squared for the acceleration in this coordinate system. The initial velocity is a positive 30 meters per second, and at the top it stops. We don't care about time, we care about the displacement. And so we're going to use the equation that doesn't have time. So that would be v final squared is equal to initial squared plus 2a delta y. And if I plug into that, what I get is c. Now I could also work this another way. I could say, well, I know if it starts with 30 meters per second and I'm taking away 10 meters per second every second, it's only going to go up for 3 seconds. In which case I could also use delta y is equal to 1/2 v initial plus v final delta t, and get the same right answer that way. So this would be C. Here we have a large truck colliding head-on with a small compact car, and this is just a third law question. The truck exerts the same amount of force on the car as the car exerts on the truck. That's just Newton's third law. That was easy. That's E. In class we saw that a diver experiences a doubling of pressure by descending about 10.3 meters in fresh water. Okay, how deep must you dive in a lake of alcohol that has a density of 790 kilograms per meter cubed to achieve a doubling of the pressure? I believe this is one of your homework problems. We just use the fact that the pressure at point 2 is equal to the pressure at point 1 plus rho g h, where h is the depth we're looking for. We start with 1 atmosphere, and we want to get to 2 atmospheres. Okay, now we can subtract 1 atmosphere from both sides, and what we get is 1 atmosphere is equal to rho g h. And that means that h is going to equal to 1 atmosphere, which is 101,325 pascals, divided by rho, which is 790 kilograms per meter cubed, times g, which is 9 meters per second squared. Okay, and what we get there is 13.1 meters, and so the answer is C. If we have a magnet stuck to a metal door of a refrigerator, which of the following forces is actually keeping that magnet from sliding to the floor? Well, a free body diagram of that magnet is going to have a weight force, Earth on the magnet. It's going to have a magnetic force. If I've got my door here and my magnet there, or my fridge here and my magnet there, so this would be the magnetic force of the fridge on the magnet. And then I would have a normal force by the fridge on the magnet and a friction force. And because it's not sliding, this would be a static friction by the fridge on the magnet. Now, in order to keep something from sliding to the floor, I better have a vertical force, not a horizontal force. So these 3 answers can't be right. And if I want to keep something from sliding to the floor, I better have a vertical force that's up. And the vertical force that's up is this friction force. That's what's keeping it up. Okay. Now, we have a 6-kilogram block sliding across the floor, and it slows from 12 meters per second to a stop in 3 seconds. What's the friction force? Well, if a problem deals with time, that's a momentum problem. I would have initial momentum plus my impulse, which is the force I'm looking for, times the time, is equal to the final momentum. If I call the direction it's moving the positive x direction, this is going to be 6 kilograms moving at 12 meters per second, is acted on by a friction force that's in the opposite direction. It's kinetic friction, and operating for 3 seconds to bring the momentum down to 0. And this gives me a friction force of 24 newtons. Okay, and so the answer is E. Now, if I go to the next page here, I have a position versus time graph, and it's of a car on a long straight road. We want to know what the car is doing. Well, first of all, we know that the slope starts out steep and then a little bit later is less steep, more shallow. And so this would be fast and this would be slow. So as time goes forward, as Mickey marches forward, this thing is going from fast to slow. Okay? Now, that means it's slowing down. So it's got to be one of these two answers. Now, we know that the velocity is negative. How do I know that? Because the slopes are negative, and slope is the velocity on a position versus time graph. If something's slowing down, the acceleration has to be opposite the velocity, and by opposite I mean the opposite direction, which for a one-dimensional problem means opposite sign. So the acceleration has to be positive. So we're slowing down. We have negative velocity and positive acceleration. So this would be C. Okay. Now we have two objects, and we have one of those objects, object A, floating with half of its volume submerged, and the other object B has all of its volume submerged. And they have identical volumes, A and B do. And so we're asked about the buoyant force on the two. They don't necessarily have the same weight. Clearly they don't, or they'd be doing the same thing. Well, we know that by Archimedes' principle that the buoyant force is equal to the weight of the liquid, in this case water, that's displaced. Okay, and that's Archimedes' principle. And since A is displacing or pushing out of the way half as much water, the buoyant force on A is going to be half as big as the buoyant force on B. So the answer to this one is B. We have here a collision problem. We have a 10 kilogram block moving to the right at 4 meters per second, and it collides with a 6 kilogram block that is also at 4 meters per second, but to the left. And we're going to conserve momentum as we do on all collisions. Since this is a vector equation, we need a coordinate system. So I would say that before the collision, I've got 10 kilograms moving at 4 meters per second to the right, so that's positive. I have 6 kilograms moving at 4 meters per second. That's to the left, so it's negative momentum. There's the collision, that equals sign. Afterwards, we're told that the 6 kilogram block is moving to the right at 1 meter per second. Okay, so I got the 6 kilogram block at 1 meter per second, and that's positive. and I have the 10 kilogram block moving at some final speed and direction that I don't know. So I'm going to make that a positive variable. And when I solve for that variable, I'm going to get V final is equal to plus 1 meter per second. And so that's going to be B. Now it's interesting to note, this is not part of the problem, but after the collision, both of these blocks have the same final velocity, namely plus 1 meter per second, or 1 meter per second to the right. That means during this collision, they actually stuck together. This is a maximally inelastic collision. Well, the reason a figure skater spins faster after he pulls in his arms is because with the skates on the ice, we isolate the system. We get rid of all the external torques such that the angular momentum is conserved. Now, angular momentum is the moment of inertia times the spin rate, or the angular velocity. Now, by pulling in his arms, he's reducing his moment of inertia, or how hard it to rotate. And to keep this equal to what we had before, the spin rate has to increase. And so he spins faster because his moment of inertia is less. So we got E. The torque here, we have the formula for torque. The magnitude is just the RF sine theta. The R is the distance from the pivot to where the force is applied. So that's going to be, I'll put it down here, 0.3 meters times the force of 400 newtons times the sine of the angle between those two directions, which would be 30 degrees. And that's going to give me 60 meter newtons. So it's either A or B. Those are the 60. Okay. Now, to find the direction of a torque, we use the right-hand rule for torque, where we start at the pivot point. That's where we're turning that nut. And we reach with the right hand out to where the force is applied. So you reach from here to there with your right hand. And then the important part of this is to turn your wrist so you can wave in the direction of the force. And that's going to force your thumb in the direction of the torque. And so this has to be, by right-hand rule for torque, out of the page. So this is B A. And I'm going to put A here. Now, we're on the last page, folks. We have a block being pulled across a rough floor with a rope such that it speeds up with a constant acceleration of 3 meters per second squared. The coefficient of kinetic friction between the floor and the block is 0.4. Turn the lights back on. And the weight of the block is 150 newtons. So let's draw a free body diagram. I have a weight force of the block, and that's 150 newtons. I have this rope, tension in the rope on the block, and that's what I'm looking for. I have a normal force, which is by the table on the block. No, it's a floor on the block. And that's got to be 150 newtons. And then I have this friction force. It's kinetic friction, so it's going to be the mu sub k times the normal force, or 0.4 times 150 newtons. And that means it's got to be 60 newtons. I'm sorry, my math skills suddenly left me. Okay, now I know that Newton's second law always applies, and so if I call to the right the positive direction, I've got the tension force by the rope on the block to the right minus the friction of 60 newtons is equal to the mass of this, which is 15 kilograms, times the acceleration of 3 meters per second squared. And that's going to give me a tension force by the rope on the block of 105 newtons. So the answer is D. A spinning gyroscope that points directly up towards the sky when it's located at the North Pole is transported to the equator while it's still spinning. Which way will it point? Well, if that's the Earth, and you have the gyroscope spinning such that its angular momentum is that way, it's omega. Remember, angular momentum is the same direction as omega. And we know that if we don't have any torques, then this angular momentum is conserved. Okay? And it's conserved in both magnitude and direction. So when you're up at the North Pole, it's pointing up into the sky, but if you bring it down to the equator, it's going to be parallel to the ground and pointing north. Okay? It doesn't have to say the same direction relative to the ground. It has to say the same direction relative to the universe. And so that means it's going to point north. So 12 is C. We have a heavy plank rests on a long table with 1/4 of its length hanging over the edge of the table. So what we've got here is a table. We got this plank, and we've got essentially 3/4 here and 1/4 here. And the largest that can be suspended from the end of the plank is 200 kilogram. So the question is, what is the mass of the plank? Well, if I draw an extended free body diagram and I use this point as the pivot, I have a force down that is going to be 2,000 newtons. And I have the weight that's going to act at the center of mass on the plank. Now, if I balance all the clockwise torque with all the counterclockwise torque about this pivot point right here, well, I have this force trying to make it go clockwise, and this one trying to make it go counterclockwise. So I have 2,000 newtons times the length of the beam divided by 4 is the lever arm. Over here, I again have the length of the beam over 4 for the lever arm there. So that's going to be the weight of the plank times the length of the beam over 4. And since they have the same lever arm, we see that the weight of the plank is going to be 2,000 newtons, just like the mass that was hanging there. And so it's going to have a mass of 200 kilograms, just like the hanging mass. So that's going to be D. This is the same problem we solved in class when we hung the 1 kilogram block from the end of the meter stick, and we found that it balanced with the pivot right there at the quarter meter mark. Okay, a radio-controlled car moving in a straight path increases its kinetic energy from 4 to 10 joules over a distance of 2 meters. Well, this is an energy initial is equal to energy final plus external. Okay. I should say the energy initial is equal to the energy final, except when it's not, and it's not when we're doing Varric. So here we start with 4 joules, we end with 10 joules, and the Varric is done by a force acting over 2 meters. And so if I solve this, I get a net force of 3 newtons. And so the answer is A. Oh, we're almost done, people. 2 football players run towards each other. One has a mass of 90 kilograms, is running a velocity of 4 meters due north. Second has a mass of 120 kilograms. He's going due south at a speed of 3 meters per second. This is exactly the same problem that we had in the other sample exam, only with Steve Iger and Greg Francis. And what we found is that the momentum is conserved, but mechanical energy is not. Okay, clearly you can see that mechanical energy, which is kinetic and potential, is not, because they had energy and then they stopped. But momentum is always conserved in every collision. So I'm going to put the answer B, and that is our sample exam.